what we're going to be talking about today is the total response of RL and RC circuits. So when we were investigating RL and RC circuits on Monday, we were analyzing circuits in which we took our independent sources out of our RL and RC networks. So today we're going to do the opposite thing. We're going to see what happens when we put independent sources into RL and RC networks. So our total response, I'm going to call this Y total as a function of time, is generally speaking of the form Yn of t, where Yn is what's called the natural response, and that's all that we looked at on Monday. And then we add to that natural response what we're going to call Yf of t. So this bit right here represents the natural response. This bit right here represents the forced response. So let's talk very briefly about what the concept of forced response means. So if we have a circuit that contains a voltage source Vs, and then we have a switch, and this time our switch is going to be closing at t is equal to 0. And then over here on the other side of the switch contacts, we have a resistor R and a capacitor C, like so. And we're interested in what's happening with the capacitor voltage as a function of time. Well, we can analyze this circuit and figure out what Vc of 0 minus is pretty easily, right? What should it be? So the switch is open at t is equal to 0 minus, which means the source isn't connected. So the voltage drop across the capacitor needs to be 0 volts. At t is equal to 0 plus, what's the value of the voltage drop across the capacitor? I disagree. It's 0 because the voltage drop across the capacitor cannot change abruptly, right? So if the voltage drop across the capacitor is 0 volts at t is equal to 0 minus, it must remain 0 volts at t is equal to 0 plus. Now, here's where we get into the forced response. The forced response is what happens to our quantity of interest a long time after the transient condition has died out in the presence of a forcing function, where the forcing function in this case is literally just that DC voltage source Vs. So a very long time after our switch has closed, our capacitor voltage should be at a level of Vs volts because it's connected directly in parallel to the voltage source Vs. Okay. So this V at infinity term here represents the forced response of our capacitor voltage. All right. So based on what we observed earlier, and by earlier, I mean Monday. The total response, actually, let's call it VC total, should be the natural response, which is what we talked about on Monday. So that would be VC at 0 plus E to the negative T divided by RC plus C at infinity. Now there's a small error here if we look at things numerically, okay? So if we were to analyze this circuit at exactly T is equal to 0, so let's put this here. So at T is equal to 0, we would have our total response, VC total, equal to, so what was the value of the capacitor voltage at 0 plus? 0. 0 E to the negative T over RC, which this whole thing just looks like 0 volts, plus VC at infinity, which was VS, or we should expect to see that the capacitor voltage at T is equal to 0 is equal to VS. This would result in a discontinuity in the capacitor voltage because it would change abruptly from 0 volts at T is equal to 0 minus up to VS volts at T is equal to 0 plus. So how we're going to fix this is we are instead going to have VC total of T is now going to be VC at 0 plus minus VC at infinity times E to the negative T over RC plus VC at infinity. Subtracting the forced response from the initial condition measured at T is equal to 0 plus makes this equation a continuous function in time. So what we would expect to see graphically for our capacitor voltage would be something like this. So this is VC of T, here's T, and we would observe something that looks like that, where we start at 0, settles at VS. So instead of having an exponentially decaying function, we have a factor of VS times 1 minus T over tau. So this is effectively just telling us how this capacitor charges. So with the understanding that we need to slightly modify our natural response in order to make this a continuous function, we're now going to have a new generic equation that we can apply to all first order circuits. So this will be valid for RL circuits and RC circuits because they behave so similarly. So we're going to have Y at 0 minus for t less than 0 minus. And then we're going to have y at 0 plus minus y at infinity, e to the negative t over tau plus y at infinity for t greater than or equal to 0 plus. So this is our generic equation that we can apply to any and every total response problem. We're going to do that shortly. But I want to talk about something else just briefly here, okay? So a question that I get asked a lot regarding this lecture versus the previous lecture is, what's the difference, okay? Which is a fair thing, because changing the direction that the switch operates effectively seems like a very subtle thing. But the difference is, in a natural response problem, we are removing independent sources from the being connected to the energy storage element. And in a total response problem, we are adding independent sources to be connected to the energy storage element. So effectively, if you analyze the circuit at t is equal to 0 plus, and there's still an independent source that is influencing the behavior of your energy storage element, you have a total response problem. If there aren't any independent sources connected to your energy storage element, you are dealing with a natural response problem. But if you don't want to go through that trouble, this total response generic equation that we've developed here works perfectly well for a natural response system, because in a natural response system, y at infinity is just 0, because there are no forcing functions making it be anything other than 0. So effectively, you can use this generic equation for literally everything, and you're just going to waste a little time analyzing the circuit at t is equal to infinity to show that things are 0, as opposed to observing whether or not there's an independent source connected to your energy storage element, okay? On your exams, if I don't ask you to do any analysis at t is equal to infinity, then it's obviously a natural response problem. If I do ask you to do analysis at t is equal to infinity, it is a total response problem. Your homework, I believe, is not nice enough to make that distinction, but I traditionally ask for the analysis at that specific time to give you an indication of which of the two generic equations that we've developed you should use. All right, so let's put this into practice if I can find the right set of notes here. Okay. Bless you. All right, so the example that we are going to work is this guy here. It's going to look like a rather large and scary circuit, but I promise you that it's not that bad. I'm going to call this terminal A and this terminal B. So in this circuit, our switch is closed at position A for a very long time before switching to being closed at position B at t is equal to 0. So effectively, at t is equal to 0 minus, the 120 volt source in series with the 10 ohm resistor is connected. And at t is equal to 0 plus, abruptly, the 50 volt source in series with the 16 ohm resistor is getting connected instead. And we're going to see how the capacitor responds to this change. While we're at it, let's also determine this quantity IR of t. Okay. So this is absolutely an example of a total response problem because there is going to be an independent source that is connected to the energy storage element, in this case, our 2 microfarad capacitor, during the transient condition. And I'm going to label my capacitor voltage BC of t like so. All right, so we are effectively going to do the exact same steps that we did on Monday when analyzing a problem, except that we're going to add an additional step. We now have to analyze the circuit at t is equal to infinity in order to get that information to plug into our generic equation. Okay, so step 1 is the exact same thing as it was previously. We analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, the switch is closed at A. And so that means we are going to have something that looks like this. And terminal B is open circuited. So effectively kind of inside this guy, we're going to have this smaller circuit. Where here's our 16 ohm resistor. Here's a 200 ohm resistor. And here is our current IR at 0 minus. So how can we determine the value of our two quantities of interest here? Our capacitor voltage DC at 0 minus and our resistor current IR at 0 minus. Mesh is valid, but it's too much work. You're putting too much effort in if you're using mesh analysis here. Yes, but we're going to use, in my opinion, we're going to use an application of KVLs more so than KVL directly. And so what I mean by that is if we look at what's connected to the 120 volt source, we have a 10 ohm resistor in series with a 200 ohm resistor. And the capacitor voltage is just the drop over the 200 ohm resistor. So I would argue that we could apply voltage division to get the value of VC in a very straightforward fashion. Regarding calculating the current IR, we have a 50 volt source in series with a 16 ohm resistor in series with a 200 ohm resistor. So we could really just use Ohm's law, 50 volts divided by 216 ohms to calculate the quantity IR. So while we could beat this thing to death with mesh analysis, setting up a system of equations and all that kind of good stuff, a quick observation of how things are connected lets us analyze this circuit using much simpler, in my opinion, circuit analysis techniques. So to restate things, VC of 0 minus is 120 volts times 200 ohms divided by 10 ohms plus 200 ohms. That's me applying voltage division there. So that's 120 times 200 over 210, which is 800 over 7 volts. And IR of 0 minus is 50 volts divided by 16 ohms plus 200 ohms, which looks like a current of 25 over 108 amps. Anybody have any questions, comments, or concerns about the analysis that we did there? If we had done mesh analysis, we absolutely should have gotten the exact same result. All right, so do you guys feel comfortable with the analysis that we did here at t is equal to 0 minus? Are you okay with moving on to what's happening at t is equal to 0 plus? All right. T is equal to 0 plus, so let's write this down explicitly. Step 2. Is to analyze the circuit at t is equal to 0 plus. And so if we look back at our original circuit, we can see that the switch is now closed at position B, and terminal A is open circuited. Okay. So I'm going to draw that like this. So let's see, we have our 10 ohm resistor and our 120 volt source like so. Here's terminal A. And then we're going to have our 16 ohm resistor in series with our 50 volt source. That's going to be connected in parallel to a 200 ohm resistor through which a current IR of 0 plus flows. This is in turn going to be connected in parallel with the second 200 ohm resistor. And then this is connected in parallel with our capacitor. So before we put our capacitor in, do we agree that this is the circuit at t is equal to 0 plus? I've redrawn it slightly here. So with that switch closed at position B, that's putting the 200 ohm resistor on the right in parallel with the 200 ohm resistor on the left. And then since the capacitor is in parallel with the 200 ohm resistor on the right, I've just included it there. So I should see 16 ohms in series with 50 volts, in parallel with 200, in parallel with 200, in parallel with our capacitor when our switch is closed at B. Are we all okay with that representation? All right. So at T is equal to 0 minus, our capacitor has a fixed amount of voltage because we know that the capacitor voltage cannot change abruptly. The current flowing through the capacitor can. So we're going to represent this capacitor at specifically T is equal to 0 plus with a independent voltage source or an ideal voltage source having the same polarity. So positive polarity on top, negative polarity on bottom, and same magnitude, 800 over 7 volts, as what we saw at T is equal to 0 minus. Okay. So how do we now determine the quantity IR at 0 plus? So current division requires us to know a known amount of current flowing into a parallel network. Since we don't have any current sources, we probably don't have any known current. We could, but that's too much work. You're 100% correct that we could do a source transformation on the left-hand side because we do have a practical voltage source. Let me ask you guys a question. The 200 ohm resistor that we're trying to measure the current through, is it in parallel with that capacitor? So we know the voltage drop over the resistor. Why can't we just use Ohm's law? We don't need to do anything more complicated than that, right? We could do something like nodal mesh, etc. But whenever we have an element that we're trying to find the current through in parallel with a known voltage, Ohm's law gets us the result we want in the simplest amount of work. So IR 0 plus is 800 over 7 volts divided by 200 ohms. So let's see, 800 over 200 is 4, so 4/7 of an amp. Because it's not in parallel with it. So what we're going to see, effectively what the 50-volt source is going to do is it's going to influence the amount of current that's flowing through the 16 ohm resistor, because on one side there's the 50-volt source and on the other side there's the 800 over 7, right? So the current flowing, let's call it down through the 16 ohm resistor, would be 800/7 minus 50 over 16 ohms. But that current flowing down through the 16 ohm resistor doesn't particularly influence the behavior of the current flowing through the 200 ohm resistor, right? Anytime we have a resistor in parallel with a known voltage, Ohm's law is all we need to calculate that current. How do we feel at, about our analysis at T is equal to 0 plus? All right. So the last thing that we are going to do here is we are going to, or excuse me, it's not the last thing, the next thing we're going to do is we're going to analyze the circuit at T is equal to infinity. So at T is equal to infinity, we effectively have the exact same circuit that we have at T is equal to 0 plus, except that now our energy storage element is going to look like its DC steady state equivalent, because we are at a time long after the transient condition has died out. So we're back at a DC steady state condition, okay? So in analyzing the circuit at T is equal to infinity, we're going to have, again, the exact same drawing as we had at 0 plus, except we replace the capacitor with an open circuit because that's its DC circuit equivalent. So here we have our 10 ohm resistor, our 120 volt source, terminal A is open circuited. Here we have our 16 ohm resistor, our, 50, not 15 volt source in parallel. The 200 ohm resistor through which a current IR of infinity flows. Here we have our second 200 ohm resistor. And we need to determine VC at infinity as well. All right. So how are we going to analyze this circuit to determine the value of IR at infinity and VC at infinity? So let me make a brief suggestion here by observing something. Our capacitor is in parallel with the 200 ohm resistor that has the current IR of infinity flowing through it, which means if we can figure out what IR of infinity is, we multiply that value by 200 ohms and we have our capacitor voltage. Or work the other way around, if we can figure out what VC of infinity is first, simply dividing that value by 200 ohms will give us IR. So we really only need to concern ourselves with finding one of these two quantities in the easiest and most efficient way, because the other one is directly related to it using Ohm's law. So, okay, so that's a very reasonable thing to do. So we can use voltage division to get the value of the capacitor voltage at infinity. To do that properly, though, we do have to recognize that we're taking the voltage drop over those two 200 ohm resistors in parallel, but that's absolutely a way that we can go. So we could say, using voltage division, that VC of infinity is going to be 50 volts times 200 ohms in parallel with 200 ohms divided by 16 ohms plus 200 ohms in parallel with 200 ohms. What's 200 in parallel with 200? 100, right? So that's going to be 50 times 100 over 116, which looks like 1,250 over 29 volts, or 43.103 volts if we feel more comfortable with a decimal. IR of infinity using Ohm's law is just VC of infinity divided by 200 ohms. So that's going to look like 1250 over 5800 or 125 over 580. This could probably be simplified further, but I'm just going to leave it like this. I know it can be simplified further because both things are divisible by 5, but I want to be lazy. 25 over 160, maybe. Yeah, doesn't matter. All right. So how do we feel about our analysis at t is equal to infinity? Anything not make sense? Voltage division may not have been obvious to everybody, but we could have done mesh analysis to get our current IR. We could have done a source transformation on the 50-volt source and the 1 kilo ohm resistor to get a single current source in parallel with 3 resistors, and then used current division to get current through the 200 ohm resistor. Or after doing that source transformation, we could have just done Ohm's law. So that current source multiplied by 16 ohms in parallel with 200 and parallel with 200 would have given us V. Lots of different ways to do it. Michael, you were raising your hand a moment ago.
So you say total response.
Right, is still connected.
So what source?
The 50-volt source is still connected. Right, the 120-volt source is open circuited, but the 50-volt source is still connected. It's not touching the capacitor, but it's still connected to that RC network, which contains the capacitor.
I'm still having trouble.
Right. So in Monday's lecture, we would have had something like this, except that the 50-volt source literally wouldn't have been here, so that VC at infinity would have had to have been 0. That's the fundamental difference. The analysis at t is equal to infinity is going to yield a non-zero answer for our quantities of interest. Okay. So any other questions regarding this analysis that we've done here at t is equal to infinity? All right. So our fourth step is to determine the time constant. During the transient condition. So we need to know what CEQ is, and we need to know what REQ is. And then we're going to plug these values in to find tau is equal to CEQ times REQ. Well, CEQ is pretty easy because there's only one capacitor in the circuit, so it pretty much has to be that. 2 microfarads. Anybody have any objection to literally writing down the number that we were told? All right. To find our equivalent resistance, what we are doing, again, I'm going to go through this very meticulously because this is a place I see an awful lot of mistakes, is we're finding the Thevenin equivalent resistance as seen by our energy storage element. So anytime we're finding a Thevenin equivalent resistance directly, we need to be dealing with a dead network, which means that both of our independent voltage sources in this circuit need to be turned off. So what that's going to leave me with is a 10 ohm resistor in series with a short circuit. So I'm just going to call it a 10 ohm resistor, where terminal A is open circuited because we're looking at this during the transient condition. I'm going to have a 16 ohm resistor in parallel with a 200 ohm resistor in parallel with a second 200 ohm resistor. And then the capacitor terminals, which are over here on the right, are the set of terminals I'm looking through to find REQ. So what do I see? Exactly right. 16 in parallel with 200 in parallel with another 200. So that's 16 times 100 over 16 plus 100, or 13.793. If I multiply this value by my 2 microfarads, my time constant is 27.586 microseconds. And I'm going to do something a little extra here. This is just a step I like to take. You don't necessarily have to. And I'm going to determine the inverse of tau. So that 27.586 microseconds, the reciprocal of that is 36,250 per second. Now we are at step 5, which is simply plug values into our generic equation. As a reminder, our generic equation, y total is y at 0 minus, t less than 0 minus. It is y at 0 plus minus y at infinity, e to the minus t over tau, plus y at infinity for t greater than or equal 0 plus.
Dr. Hartman,
Yes.
do you not need to add the 10 ohms to the equivalent resistance?
That's a good question. You do not, because one leg of the 10 ohm resistor is open circuited, so it cannot contribute because it's not part of a path that could carry current.
Okay, thank you.
So from here, we could say that VC of t. So what was the value of our capacitor voltage at t is equal to 0 minus? 800 over 7. Thank you. And then we would have here 800 over 7 minus 1250 over 29. E to the negative 36,250t plus 1250 over 29 volts for our capacitor voltage. And we could plug in the values for our resistor current at 0 minus, 0 plus, and infinity into our expression to get that as well. But because this is at the bottom of the page, I'm not going to bother doing that. Okay. At this point, it is literally just plug in the results from steps 1 through 4 into this generic equation And if you've done all of your circuit analysis steps correctly, that answer has to be right. All right, so today we've talked about how to handle the case where we have independent sources left in our circuit during the transient condition by including what's called the forced response into our response equations. We have developed a new kind of catch-all general equation that we can use for both total response problems and natural response problems if we cannot easily identify which one we're dealing with. And we have worked an example explicitly with a capacitor in it because I didn't get a chance to do that on Monday, and shown that at t is equal to 0 plus, you treat capacitors like ideal voltage sources having the same polarity and magnitude as the capacitor voltage at t is equal to 0 minus. Are there any further questions about what we've done for today?
Just to, for my sake, like, just to clarify, the only thing we did different between this and ENGR and Monday was, one, we added another step in analyzing circuit T at
Infinity.
infinity.
Yes.
Then two, we have the independent source, instead of like shorting the voltage sources for circuiting the current sources.
So I don't particularly like how you phrase that last thing because I'm confused by it. Okay, so let me be explicit here. The only time that we would ever short an independent source or open circuit an independent source would be when we're calculating our equivalent resistance, because we're looking at a dead network. So that's just an application of the Thevenin and Norton equivalent circuit that we did at the beginning of this section of the class. So that's the only time we're ever going to turn off any independent sources.
So literally the only difference is we just have one more step at this point.
Yep, one more step, analyzing at t is equal to infinity, and then using our new generic response equation. That's correct. All right, so since nobody else is saying that they have any problems, I'm gonna let you guys work on your in-class assignment. If you have any questions or anything, I would be happy to help. Yes, sir. 3,600, 250, that's literally the reciprocal of tau. So it's tau to the -1 power. And the reason why I get that is because I know right here, let me put a circle around it. This bit right here is just -t times tau to the -1 power. Because t over tau is the same as t times the reciprocal of tau, right? And I do that because I don't like to have fractions in my exponent. That's it, in my exponential function. So I take the reciprocal so that I get, yeah. So that's just me liking that form slightly better than having a fraction there. Does not matter which way you choose to go.